Hey, welcome guys. Yeah, I just changed my background, which is yeah, very interesting. Okay, so today let's talking about the generalization of the Weierstrass theorem and into the algebra, the more abstract algebra. So basically, what we already proved is that in the AB, right? So basically, the conventional Stone Weierstrass is a continuous function defined on closed interval. So continuous function f on AB can be approximated by a polynomial. Okay, so this is the key idea. Or basically, you can say that there exists a polynomial Pn of x such that for epsilon greater than 0, your Pn minus f, you take a sup x belongs to AB, can be arbitrarily small. Or another way is to say that, this is the same as so basically you can find a Pn, which Pn approach to f as n goes to infinity. Okay, and this approach to f in this matrix space, in this matrix sense. So in this matrix sense. Okay, so yeah, well, basically, as I say, if you can define L of k as an order continuous function from k to. If you haven't seen my previous video, then you should check it. F from k to compact, the real number, and which is a continuous and bounded. Oh, by the way, since k is compact, so it's automatically bounded if f is continuous. So and you can define a distance f minus distance dfg defined to be f minus g, where you take sup x belongs to k, and easy to prove that this is a matrix space. So basically, that's why you can say that Pn converges to f as n goes to infinity in matrix space L of AB. Okay, and easy to generalize this into higher dimension, right? So basically, you can, I mean, if you have any polynomial defined on let's say on a hypercube, then you can find a multivariate polynomial which approximate to f up to any degree. Okay, but today we want to generalize this theorem into more abstract setting. Okay, so in order to do this, we need to define many ideas. Okay, so definition. Definition is that let's say we have A is a family of complex function. A is a family of complex function. So basically, just some complex function. Okay, define on set E. Okay, so in my setting that E is just some subset of matrix space. So X is a matrix space. Okay. And which we have one such that for all f g belongs to A, if f plus g belongs to A, and the second is that cf belongs to A for all c belongs to complex number, and the third is that suppose f times g belongs to A, then we say that A is algebra. We say that A is algebra. Yeah, so basically close under addition, multiplication, and yeah, constant multiplication and multiplication. Okay, and also this is the definition. And the first another definition is that if whenever any fn approach to f uniformly convergence. So uniform convergence need to apply. In general, uniform convergence need to define on matrix space, right? Because you want to say that for epsilon greater than 0, you will need metric. Okay, so if whenever fn uniformly converges to f, and if f belongs to A, then we say A is uniformly closed. Okay. Okay. And so basically, if somebody give you any algebra A, right? And then you can take a B, you can define a set B, which is all the, let's say B is F, which F is a limit, where F is a limit of uniform convergence of convergent sequence of members in A. Then B is called a uniform closure of A. Okay, this is our definition. So basically, given A, you can collect all the uniform convergence sequence of A in A and define a uniform closure. This is the same as, I mean, you can define all the convergence sequence in the rational numbers, and then you define this is just real numbers, right? So basically, you can take all the uniform convergence sequence. If F is a limit of uniform convergence sequence in A, then you define it's called a uniform closure. Okay, so basically we have uniformly closed and a uniform closure. Okay. Okay, so now we have a theorem. This theorem is simple. So let's say if B is a uniformly closure of an algebra A of bounded functions. So now I add a condition which is bounded. Okay. But then and B is uniformly closed algebra. Okay. Yeah. So okay. Super. Okay. So let's just say that B is uniformly closure algebra of A. So you collect all the bounded function and say that, oh, this is A, which is algebra, and B is a uniformly closure of such algebra, and B is uniformly closed algebra. Okay. So the key idea is that you just need to prove that if Fn uniformly converges to F, Gn uniformly converges to G, and you want to prove that F plus G in B and Fg in B and the Cf in B. This is almost trivial. The reason is that if we have this, then we can easily the deduction that Fn plus Gn will converge to F plus G. Standard analysis, Fn Gn converge to Fg, and Cfn converge to Cf, and which is the bounded makes sense, right? If you use bounded, then you can easily prove these three, and you arrive at the results. Okay, so this is almost a trivial. Okay. Oh, let me just say a word that I haven't said. So once I define this, then I can say the results. I can say the Weierstrass. So I can say the standard Weierstrass, or the simplest version of Weierstrass says that the set of continuous function, define AB. Yeah, so some guy will have this notation. Okay, so the set of continuous functions C AB is the uniform closure. A uniform closure of polynomial on AB. Okay, this is what we just proved, right? Because any CAB can be viewed as any continuous function can be viewed as you can find a polynomial which arbitrarily close to it, right? So basically, it is just the same sentence. Okay. Okay, so now let's working on some other definition. So this definition is also interesting. Amazingly, I haven't seen this in undergraduate when I was undergraduate. Okay, so let's say A is a family. So also A is a family of E. A is a set of function of A is a family of function defined E. Okay, so in this case, A should be complex. Okay, and if if any x1, x2 belongs to E, and then they are not the same. If there exists F such that F belongs to A such that Fx1 is not the same as Fx2. So this is stupid. This will just say that you can find some F which you can distinguish these 2 points. And we say that A is a separable, A is separable points on E. Okay. So A is a say to separate points. Separates points on E. Okay, so this is definition 1. And the second definition is also simple. If for each x belongs to E, there exists f belongs to A such that f of x is non-zero. This is all stupid, right? It's just say that, oh, for each point, you can find something is non-zero. Okay. And then we say that A vanishes, no points of E. Okay, so we have two definitions. One is a separate point on E, one is no point of E. Okay, and yeah, let's say some example. So this example is also yeah. So example is that the polynomial, right? All the polynomial on AB satisfy these two. Okay, satisfy these two. This is trivial. Okay, you can prove by yourself. Okay, and there's an example. Suppose you only talk about if you talk about an even function, if you only talk about even function, then you say that, and you see that x and negative x cannot be separated, right? So this is the non-example. Also, if you're talking about odd function, your f of x is always 0. Okay, so if you're talking about even function, then even function is no point of E, but non-separate point on E. If you're talking about odd function, which odd function is a separate point on E, but no point of E. Okay. So you can see that these two are very interrelated in the polynomial case. So which indicates combine these two ideas, you should have the better theorem. Okay, so there is a theorem that I think is important. So let's talk about, and very simple. So A is suppose A is a set, right? A is a family on E, but with the separated point, so separate on E, and the vanishes of E, but no vanishes of E. So that satisfy the previous two conditions. And suppose let's say x1 not the same as 2 of, and both are the points of E. And given C1, C2 are constant. So if you're talking about a complex, talking about real is irreal. Then then you can find a function. Then there is a function f belongs to E, A such that f of x1 is C1, f of x2 is C2. Okay, so yeah, so this is the very strange results at very strange results. Just tell you that if you have these if you have these two conditions, right, somehow that you given any 2 points, right, you can assign any values to this x1 x2, right, such that you can find f which pass it. Okay, and this f need to be always exist. Okay, so this is a very powerful result because I do not assume many structure of A. I only say that A is algebra functions. Okay, A is algebra. So A is algebra function. Okay, so the proof is notice that there exists a G, right? So Gx1 not the same as Gx2. Reason is that things separable points, and no vanishing. So there exists the H and the K, such that Hx1 is non-zero, Kx2 is non-zero. And you can define U to be Gk minus Gx1k, and also V to be Gh minus Gx2h. Okay, so and easily show that the Ux1, which is Vx2 0, but the Ux2 non-zero and the Vx1 non-zero. Okay, and you just define F to be C1 V Vx1 plus C2U Ux2. Okay, so let's say this is F, right? So easy to see that if Fx1 will be CVx1, C1 Vx1, Vx1, So this cancel, and ux1 is 0, right? ux1 is 0. So fx1 will be c1 and fx2 will be c2. Okay, so very simple. Yeah. Theorem. Theorem says that A is an algebra of real functions. So A is an algebra of real functions. Okay, so the standard example is a polynomial. Okay, on a compact set, on K, which K is compact, and also we have that A is a separable points on K, and vanish no vanish point on K. So also all the standard. Then the okay, sorry, it's a not real function, real continuous function. Okay, then you can define and uniformly the uniform closure of A consists of real continuous function on all functions on K. Okay, so this is the final theorem that I plan to prove. So this theorem is a generalization to the standard stone Weierstrass. Okay, so for stone Weierstrass, okay, so let me just write down. I say everyone knows what I'm talking about. For stone Weierstrass, take K to be AB, and then your A family of algebra, I take all the polynomial on AB. Okay, so A is an algebra of continuous real continuous function, polynomial is continuous, and there's separate points on K. Sure, A vanish point of K, sure. Then uniform closure of A consists of all real continuous functions. Yeah, so this is the generalization. Okay, so proof is a little bit long, but we can use our previous results. Okay, so step 1. So step 1 it says that if let's say f belongs to B, if f belongs to B, then absolute value belongs to B. Okay, so this means that if f belongs to the uniform closure of A, then the absolute value function will belongs to the uniform closure of B of A. Okay, and the proof is just very simple. You just let A to be sup f of x. Let's say x belongs to K, and by a stone Weierstrass. Is it stone Weierstrass? Okay, so yeah, by stone Weierstrass, right? So absolute. Okay, so by a stone Weierstrass, there exists C1 up to Cn, which are all the reals, such that the Ci, Yi, I from 1 to n, y is less than epsilon. Okay, so this is the stone Weierstrass, right? So there's a polynomial, and you can prove that if you're talking about absolute value function, then you can eliminate the first term. Okay, so simple exercise. Okay, so you just that so this is using the I should say the simplest version of the stone Weierstrass. That let's say the G to be Ci, Fi, I from 1 to n. Then we just show that so this just tell me that G of x minus f of x absolute value less than epsilon. Okay. Yeah. Oh, by the way, this y is any points belongs to this. Okay. So take any points belongs to this, then you will have these results, right? By the simplest stone Weierstrass, and you define G to be this CIFI. Oh, by the way, G is a function, right? So G of x minus f of x, right? Just plugging, then you get this. Okay, so which show that f belongs to B, right? Because now now it's uniformly closed. I know that this is uniformly closed, right? So okay, so since B is uniformly closed, so f absolute value of f will belongs to B. Okay, so step 2, f belongs to B. If f belongs to B and G belongs to B, then the max of fg belongs to B, and the mean of fg belongs to B. Okay, so proof is simple. Okay, so by the way, max of fg means that yeah, I mean given x, you can check whether one is maybe take the larger one. Okay, yeah, okay. I think I don't have to write proof. Okay, so proof, I don't have to write a definition. Okay, so max, you can easily check the max fg will be f plus g divided by 2 plus f minus g absolute value divided by 2. Okay, so obviously then when f greater than g become f, when g greater than f, it becomes g. And the minimum of fg is also simple, just f plus g divided by 2 minus f minus g divided by 2. And by the previous, since A is algebra, right? So this belongs to A, this belongs to A, this belongs to A, this belongs to A by the previous lemma. So all of this belongs to A. And also if it belongs to B, right, then you can find F and converge to F uniformly. And yeah, easy to prove by the lemma 1. L belongs to B because if you can find Fn converge uniformly to F, Gn converge uniformly to G, then Fn plus Gn will converge uniformly to F plus G, and by the lemma 1, the absolute value doesn't change the results. Okay. Yeah, so yeah, you can see this, and you can also see Fn minus Gn approach to F minus G. Right, so F minus G belongs to B, and by the lemma 1, the absolute value of F minus G also belongs to B. Yeah, so this is a proof. Okay, and then you can easily generalize into n of length, right? Because the maximum of FGH will the same max of F max of GH. Okay, so you can generalize to n of length, and it's also true. Yeah, I mean these step are just both trivial. Okay, so step 3. Step 3 a little bit non-trivial. Okay, so let's talk about it. So given any real function, let's say f is real continuous on K, so real and continuous on K, and x belongs to K, and for epsilon greater than 0. Okay, so this is condition. Then there is this gx belongs to B, which gx is f of x, and gxt is greater than f of t minus epsilon. T belongs to K. Yeah, this probably the weird step. Okay, so let's say that you can find a gx, which is a function. I label x such that g is x. At that point, x is the same as f, right? But for other t points, which will be slightly larger than f. Okay. So I mean, you see this condition, you know that I should use what? I should use the vanishing, no vanish points of E and the separate points on E. Okay. Okay. So proof. Okay, I mean I can use the previous lemma, right? And previous lemma. So there's a lemma that says about the condition that the no points and the vanish points. Okay, so this condition says that let's say let's say okay, so let's first see. So okay, so let's go step back, right? So in this case, the A separate point on E, a no vanish point of E. Okay, so you can easily say that if A satisfies this relation, then the uniform closure of A is also satisfied. Okay, so B also satisfy these conditions. B also satisfy these two. Okay, simple exercise for you to check. Okay, so that means for any y belongs to K, right, you can find the function hy belongs to B, such that hyx is f of x, and hyy is f of y. Okay. Okay, but hy, okay, so now hy is continuous, right? because hy belongs to B. Okay, so hy is continuous. Okay, so there is the open set jy. Let's say you have y and jy. Okay, open set. This is open set jy such that hyt greater than f of t minus epsilon, where t belongs to jy, right? Because this is continuous. And I know that now the key is also now since k is compact, which is a key, so can be covered by jy1, right? Union jy2 up to some point jyn. Okay, so then they just take a g of x to be the max of this hy1, hyn, right? And previously I already proved by a step by using the step 1 and step 2. So all this hy1 already in B, right? So the gx will be in B. Okay, so yeah, that's it. Okay, then since this is compact, right? So you can take finite of length. So you just pick I think the pick minimum of this epsilon, right? Okay, so step 4. Step 4 says that if f is so if f is real, continuous, on a compact set K, and we are going to prove the results, right? For any epsilon greater than 0, there is this function h belongs to B, such that h of x minus f of x is less than epsilon. Okay. Yeah, this is the result, right? The uniformly closure of A will be any continuous, can be arbitrarily close to any continuous function. Okay, so this is what we're gonna prove. Okay, so now since we already have all the theorem, right? So the proof should be simple. By the lemma, by the step 3, right? There is the gx. Right, for each x, let's say from the previous theorem that the gxt less than f of t plus epsilon, right? And let's say for t belongs to vx. The reason is that gxt is continuous, right? So for this x, I can find the open neighborhood such that this gxt satisfies this relation. Okay. And also do the same trick, right? So k is covered by all this v, finite of length, right? Because k is compact. So and then you take h to be the minimum of gx1 up to gxm. Okay, so by the previous lemma, you also proved that h belongs to B. Okay, so from here you just get h, right? So right, h less than f of t plus epsilon, right? So h. Okay, so this is the one step, right? So but by then, let's say then by step 2, your h belongs to B and can be also satisfy the h of t greater than f of t minus epsilon. Okay, so the key step is that this gx come from step 3, right? So in the step 3, okay, so in a step 3, in a step 3, I already construct this gx. Let's see where, right? In a step 3, right? I already construct this gs, and this gx satisfies greater than f of t minus epsilon, right? This is f of t, and this is f of t minus epsilon, right? So it's dodged here, right? And but due to continuity, right? I can demand this g of x less than f of t plus epsilon. Okay. For some t belongs to vx. The reason is, okay, so you might think, oh, why this is true? The reason is that this gx is f of x, right? So that means in near of x, at that point x, they are the same, right? So if they are larger, if you're larger a little bit, then you can demand that your gxt less than f of t plus epsilon. Okay. But if you combine these two, you get g of x larger than f of t minus epsilon, and you get h of t minus less than f of t plus epsilon, right? So combine these two, right? You just get an answer, right? You h of t minus f of t less than epsilon. Okay. Yeah, this is the proof. Oh, okay. Okay, so very happily we proved the generalization of the Stone-Weierstrass by the 4 steps. Okay, so let me just keep going, saying something interesting. Okay, so the key step, there's a results that the theorem, this Stone-Weierstrass, right? This Stone-Weierstrass does not hold for complex value function. Okay, so remember in my proof that I assume that f is real. Okay, so that I can use this plus epsilon. Okay, so this is a very key. And the reason is that I use absolute value, right? And the maximum and minimum. Okay, so it's not clearly, it's not immediately to see why the complex will fail. So this is not simple example. Okay, but I just want to mention that the Stone-Weierstrass does not hold for complex value functions in general. Okay, but there's a theorem to help you. Okay, so theorem says that okay, so let me just give a definition. Okay, so I define A. So now A is a family of it's algebra of family of complex functions. Let's say if A is a self-adjoint, if f belongs to A, then so basically if f belongs to A, then the f complex conjugate will belong to A. So this is called self-adjoint. That's very simple definition. Okay, so theorem says that suppose f is a self-adjoint. So now self-adjoint is the missing part. Self-adjoint algebra of a complex continuous function f. Let me just write everything clearly. Continuous complex continuous function on compact set K. Okay, and also you need another condition, same as previous. Sorry, A, and A is set 2 conditions, right? No vanishing on K, and separates on K. Then, okay, so we spend a lot of time, we talk about then the uniform closure of A, let's call it B, contains all complex continuous function, Okay. Okay, so this is the generalization of Stone-Weierstrass in the real version. The complex version, the only difference is that I added something called self-adjoint. Okay, so quick proof. Okay, by the way, there's also another way to saying this is that A is dense in L of K. Yeah, so the key idea, let's just quickly prove it. So key idea is that you can define AR to be the set of all real functions on K which belongs to A. So I should say AR is all the reals. Let me just quickly, all reals functions belongs to K, belongs to A. And then now let's say F belongs to A, right? And so F can be written as U plus IV, where U is UV are real. And easy to, so, and the 2u is f plus f conjugate. And I know that since A is self-adjoint, right? So A is self-adjoint, A self-adjoint. So this guy belongs to A, this guy belongs to A. So U belongs to A. Okay. So now you can see the proof, right? Because U belongs to A. So right, so U belongs to AR, right? So that means you can right. So and just using the same result, if x1 not the same x2, there exists f belongs to A, such that fx1 is 1 and the fx2 is 0. Okay, and you can get the ux1 is 1 and the ux2 is 0. Okay, from here, right? Because f is just f plus f conjugate is 2u, right? So you can easily get, if you have these two conditions, then you get these two. And from here, you can get AR separates points on K, right? AR separates points on K. Okay, so question is that the key why I want to say this here part is this part is that my definition only say that A separates points on K, right? If I take a sub algebra of AR, I did not say that AR separates points on K. So AR is a sub algebra of A, and the property of A do not inherit to its sub algebra. Okay, so from here you just prove this, and you can easily say that you can easily see that AR vanishes at no point K. Okay. The reason is that let's say if X belongs to K and the G of X is non-zero, right? For some G belongs to A. Okay. Then you also know that there is a complex number such that the lambda G of X greater than 0. Right? And you can check this. Okay. So let's say if F is lambda G and F is U plus IV, then you can easily show that U of X is greater than 0, right? Because lambda G is greater than 0. Very stupid, right? So so lambda G is greater than 0. So if you take the real part of U, then the U of X is greater than 0. Okay, so we should prove that the AR vanishes no points, no points of E. Sorry, of K, no points of no point vanishes no points of K. Let me just okay. So now you already you proved that this real algebra, right, inherit from all the good property of A, right? And then you can prove your you can use the previous theorem, right? Use AR so that every real continuous function defined on K is dense, right? Sorry. Every real continuous function defined on K is in a uniform closure of A, R. A. Okay, right? So which prove that every real continuous function defined on K is in A, is in uniform closure of A. Because in uniform closure of AR, but AR is a subalgebra of A, right? So it's also always in a uniform closure of A. Okay, so you prove the real part is a uniform closure of A, right? Guess you can easily show that the imaginary part also is real. It's also in a uniform closure of A. Similar approach. Okay, so also let me or one just say that, let's say F is U plus IV, right? So now U belongs to B, right? And F belongs to, sorry, also V belongs to B, right? So F belongs to B. Okay, so hope you guys like this video, and if you see up to here, then you are truly my fans, right? You should subscribe to my channel. Okay, so see you guys next videos. Subscribe to my channel. Bye bye.